Hi everyone, my name is Junchang Li, a PhD student from University of Electronic Science and Technology of China. I'm very excited to present our work on ECFuzz, effective configuration fuzzing for large-scale systems. I will show our work from the above three parts: introduction, ECFuzz, and conclusion. Large-scale systems often have many configurations. Configuration is another program input that directly controls the behavior of the program, and it usually has two manifestations: the command line option and the configuration file. Here we give the corresponding examples, respectively. Once the large-scale system is configured incorrectly, it can also lead to serious consequences. For example, in April 2020, the SM-4 rocket model of SpaceX suffered body damage because of a configuration error. And in recent years, large internet companies have suffered widespread global outages caused by configuration errors. So it's very important to ensure the configuration security of large-scale systems. However, this is difficult because configurations in large-scale systems have their own features. Feature 1 is relational complexity. A single configuration has construct relationships. For example, for a certain configuration A, its type may be numeric or string, and its value should satisfy its type constructs. However, in addition to construct relationships, there are also dependency relationships. Dependency relationships refer to conditions that should be satisfied between different configurations. Take the control dependency as an example. If configuration B takes effect only when configuration A is true, we say there is a control dependency between the two configurations. As shown in the figure above, we also give its corresponding code patterns. In this case, if we want to mutate configuration B, we must first set configuration A to true. Otherwise, the mutation made for configuration B will not take effect. Feature 2 is time capacity. For larger scale systems, the time cost for system testing is high. The above table shows the speed gap between different scale programs. We find that the average speed of system testing in larger scale systems is several orders of magnitude slower than small scale programs. So once a configuration that is unlikely to yield errors has been generated, lots of time for system testing will be wasted. However, existing configuration testing techniques do not consider the above two features. As shown in the figure above, first, existing configuration testing techniques generate new test cases through configuration generation. It is divided into two steps. Step 1 is selecting a single configuration from candidate configuration set. Step 2 is generating a new value according to its construct relationships. There are two problems with existing configuration generation techniques. If only a single configuration is considered in each fuzzing champion, it means that only limited code related to the configuration can be fuzzed each time. Moreover, in larger scale systems, dependency relationships also need to be considered. Ignoring dependencies will result in invalid configurations. After using configuration generation to generate a test case, the existing configuration testing techniques directly inject the test case into the system testing to complete configuration validation. However, the speed of system testing in larger scale systems is extremely slow. Once a configuration that is unlikely to yield errors has been generated, lots of time for system testing will be wasted. So, how to solve the above problems? Overall, we have two contributions. We respectively propose the multi-dimensional configuration generation strategy and the unit testing-oriented configuration validation strategy to solve existing problems of configuration generation and configuration validation. Finally, we experiment a prototype of ECFuzz. Next, I will introduce the design details of ECFuzz. For multi-dimensional configuration generation strategy, multiple configurations are first selected from the candidate configuration set. The selected configurations are divided into two categories. Category 1 is some randomly selected configurations, for example, COF-A. Category 2 is configurations that have dependencies on Category 1, for example, COF-DA. Here, the dependency relationships table we used comes from CDEEP. Then, ECFuzz generates new values based on their dependency relationships. Similarly, take the control dependency as an example. If configuration DA takes effect only when configuration A is true, we say there is a control dependency between the two configurations. In this case, if we want to mutate the configuration A, we can directly mutate it according to its constructs. If we want to mutate the configuration DA, we must first set the configuration A to true and then mutate it according to its constructs. After generating test cases, ECFuzz needs to effectively validate these test cases. As mentioned before, the speed of system testing in larger scale systems is extremely slow. Fortunately, the speed of unit testing is acceptable compared to system testing, and mature larger scale systems have relatively complete unit tests to check whether the program unit can correctly implement the functions, performance, and constructs in the detailed design specification. So we can use unit tests as a proxy to system tests to do an initial test case reduction to whip out configurations unlikely to yield errors. Based on the above ideas, we have designed a unit testing-oriented configuration validation strategy. ECFuzz automatically obtains the corresponding unit tests through the mapping relationship between configurations and the unit tests. Among them, the mapping relationship we used comes from ctest. ECFuzz executes the corresponding unit tests and monitors their running results in real time. The test case that fails to pass the unit tests is put into the system testing. If the system testing still fails, a potential error has been found. Before showing the results, we describe this experiment setup. The comparison objects include other tools and self-comparisons. We measure target through effectiveness metrics for evaluation, including quality of test cases, types of exceptions, and bug counting. And we choose 5 mature and widely used larger-scale systems as the systems on the test, including HCommon, HDFS, HBase, Zookeeper, and Alloxil. We show the evaluation of ECFuzz by answering the above 4 research questions. RQ1 is multi-dimensional configuration generation strategy evaluation. We merely compare ECFuzz with ECFuzz. For quality of test cases, ECFuzz finds 71.9 more unspent failures when the same 1,000 test cases are injected into the system. For types of exceptions, ECFuzz finds 9 more types of exceptions compared to ECFuzz. The results show that the effectiveness of using the multi-dimensional configuration generation strategy. RQ2 is unit testing-oriented configuration validation strategy evaluation. We merely compared ECFuzz with ECFuzz W. ECFuzz builds 54.1 more unexpected failures when the same 1,000 test cases are injected into the system. The results show the effectiveness of using the unit testing-oriented configuration validation strategy. Compared to the state-of-the-art configuration testing techniques, ECFuzz outperforms them in terms of quality of test cases and the types of exceptions. For unknown bugs evaluation, ECFuzz has detected 14 previous unknown configuration-induced bugs. Only 8 of them can be exposed by existing configuration testing techniques. Moreover, 5 of them have been officially confirmed. In this paper, we propose ECFuzz which effectively tests configurations in larger-scale systems by improving the process of configuration generation and configuration validation. Moreover, we have conducted extensive experiments on real-world large-scale systems. The results show that ECFuzz achieves significant improvements. The code of ECFuzz is available on GitHub. Please contact me by email if you need any help. This is the end of my talk. Thank you for listening.